Hi students, today we will learn about synthesis of alkenes using acetylenes. Acetylenes are simplest alkyne, readily available and they are colorless gas used as a fuel. So let us study about the introduction. Acetylene itself is readily available and its first important property is its ability to form an anion 1, usually with sodamide, in liquid ammonia and also by exchange with Grignard reagent. Sodamide is a very strong base which is used in organic reactions for the deprotonation of terminal alkynes. This anion formed can react with alkyl halides, carbonyl compounds, and oxides to give intermediates as 2, 3, and 4 respectively. These products, that is 2, 3, and 4, still have an acetylenic proton so that they can again react with a base and an electrophile to give similar products. That is here, when you look at this product, that is 2, here you can see again there is another hydrogen, a proton, acidic proton, and this can again further react with the sodamide, and there can be an anion of this kind generated, and this can further react with ketones or alkyl halides, or it can also react with epoxides. And once it reacts with a ketone, it's going to give rise to a product as this kind. There's a formation of a hydroxyl group, alcoholic group. Now let us look at some examples. So the first one is the target molecule 1. So here you can see that there is a triple bond in this target molecule. So now what we will do is we can disconnect the bond that's formed between C2 and C3, and we can write down as CC disconnection about the retrosynthetic arrow. Now the synthons for this would be an acetylene which is having a negative anionic acetylene, and also there would be a cationic group here. So now the synthetic equivalents for these two would be acetylene, that is a negative charge on acetylene is going to grab a proton and it is going to form an acetylene as this kind, and the synthetic equivalent for this cation would be the formation of an alkyl chloride or an alkyl halide, that is a Cl minus or X minus is going to attack the positive charge of this carbon and it would give rise to an alkyl halide, and here it's an alkyl chloride of this kind. Now coming to the synthesis, the first step would be the deprotonation of acetylene. Otherwise, there wouldn't be a further reaction for the extension of a chain, carbon chain. And hence, what we have to do, first step would always be reaction of an acetylene with sodamide. Sodamide, since it is a good base, it is going to deprotonate hydrogen, giving an anion. That is, an acetylic anion is going to be generated. Now this is going to further react with an alkyl halide. As we know, the nucleophilic carbon is going to attack the electrophilic carbon, that is the carbon which is bonded to chlorine, as chlorine is highly electronegative and carbon attached to chlorine would be electropositive, and hence this nucleophile, this acetylenic anion would attack the electropositive carbon, and there would be the elimination of chloride ion. So here what happens is, here there is an elimination of H plus, minus H plus, and here there is Cl minus, and hence it would give minus HCl. And once the reaction happens, it is going to give rise to the target molecule. Now there's a bond formed between the acetylic anion and the carbon, and hence there would be this target molecule 1 which would be generated. Now let us take another example, target molecule 2. So here we have an alkene, and we also have a alcohol group which is there in this target molecule 2. So the first step would be always the functional group interconversion of an alkene to alkyne. So now why we should do a functional group interconversion from alkene to alkyne? So now we know that in alkyne there is a 50% of S character and 50% of P character. Whereas in alkene, that is an sp2 hybridized, it is having 75% of P character and 25% of S character. Now when you look at alkyne, here as I told, it is an sp hybridization in alkyne, and it has a 50% of S and 50% of P character in it. Now once you disconnect a bond between the acetylene group and the adjacent carbon atom, it is going to give rise to an anion, right? Now this anion can be stabilized, that is this part can be stabilized only if the nucleus is very close to the negative charge. That is the positive charge on bearing the nucleus is close to the, there's a positive charge, that is nothing but the nucleus is close to the negative charge. Only then this anionic species can be stabilized. So hence we usually tend to convert the alkene to alkyne. And also why we, the second reason why we convert to alkyne is acetylene is a very good starting material. It is easily available. It is the simplest alkyne and there is no need to, further disconnect it any furthermore. So hence these are two reasons why we, whenever there is an alkene in a target molecule, we are going to first do the functional group interconversion to an alkyne, and then we are going to disconnect so that we're going to get an acetylene as the starting material. So these are the two reasons. So now once we disconnect the acetylene, you're going to get two synthons, that is nothing but the acetylene anion, and you're going to get a synthon which is having going to be a cation. Now we know that the synthetic equivalence would be an acetylene itself, that's the alkyl group attached to the acetylene, and also it is going to be an epoxide. So these two are going to be the synthetic equivalents. Now here you can see how this intermediate can be still further disconnected. That is, it is nothing but a propyne. It can be, it's a butane. Butane can be further disconnected further to give rise to two synthons. That is, there is going to be disconnection just beside the acetylene and the carbon which is attached to the acetylene group, and this is going to give rise to two synthons. That is again going to be a ethyl group, ethyl cation, and it is going to be the acetylene anion, and their synthetic equivalents would be an bromoethane, and it is going to be acetylene. So these two are going to be the starting material. So make sure that wherever you have an acetylene which is linked to a further higher carbon atoms, or like a butane or a pentane, so make sure that you can further disconnect it to an acetylene group, and then you can have the other fragment. So here, since you had a butane, you're going to disconnect it further to give an acetylene and an ethyl group. So here this ethyl cation is going to have a bromide group attached to the positive charge, and it is going to give rise to ethyl bromide, and it is going to give rise to acetylene as the starting material. So these are going to be the starting material. Now you can make use of these two as a as a starting material, and you can easily find the target molecule, you can produce the target molecule too. So how is that going to be? You have the acetylene group. Again, you are going to make use of sodium nitride sodamide to deprotonate the hydrogen bearing the, that is, which is bonded to the acetylene group, and this would give rise to an acetylene anion. And now this can easily react to the, or it can, since it is a nucleophile, it can easily attach towards the electrophilic carbon, that is a carbon which is bonded to the halide group, and there would be departure of the bromide ion. So there's departure of H plus, minus H plus, and minus Br to give rise to minus HBr is going to be eliminated, and you are going to get an intermediate of this kind, that is nothing but a butane is again generated. Now this butane, again further you have to disconnect it, you have to react it with sodamide, because again we need an acetylene anion to again further react with the epoxide group. That is only possible when there is a reaction with the sodamide, that is, it is going to deprotonate the acetylene. Once it deprotonates, again you're going to have a negative charge on the acetylene group, which is again going to react with an epoxide, and here there's going to be a ring opening. That is the three-membered ring, that is the epoxide, is going to have the ring opening, and it is going to give rise to the molecule. Sorry, it is going to give rise, it is not going to give rise to target molecule, it is going to give rise to an alkyne group. Now here, since the target molecule is an alkene, so and we have an alkyne, what we are going to do is we are going to make use of Lindlar's catalyst, and we are going to further reduce the alkyne to an alkene. So now here there's another advantage of using Lindlar's catalyst. See, Lindlar's catalyst is usually used for the hydrogenation of alkynes to alkenes. Now, once you use the Lindlar's catalyst, it is going to be stereospecific. It is not going to further react, or it is not going to further reduce the alkenes to an alkane. So hence, we are going to make use of Lindlar's catalyst because there's only going to be a one-step reduction. That is, an alkynes is going to be reduced to alkenes. The alkenes is not going to get further reduced to alkenes. So this is an advantage of using Lindlar's catalyst. That is using in presence of hydrogen. So that is, we are going to hydrogenate the alkynes to alkenes, wherein there's no further reduction of alkene. So hence you are going to get an alkene, and this is going to be the starting material, that is the target molecule 2. So this is how you can make use of Lindlar's catalyst. So write down Lindlar's catalyst whenever you have to reduce an alkyne to an alkene. Next we have target molecule 3. So here we have, you can see an ester group here as a target molecule, function group, and also you have an alkene. So first, whenever you have an ester, it is very much suitable to disconnect an ester because we can get an carboxylic acid and alcohol as a starting material, and which is easily available. So hence, first step would be a CO ester disconnection. We're going to disconnect the carbon and the oxygen which is attached to it. So that is nothing but going to be a COS bond. That is nothing but it is an example for CX disconnection. So once you do the CX disconnection, you are going to get two synthons. One synthon, that is an oxygen, is going to have a negative charge, and the other would be a carbonyl cation. So here their synthetic equivalent would be an alcohol group, and the other synthon would be an acid chloride. So these would be the synthons, synthetic equivalents for the corresponding synthons. Now next step would be, what we would do is we would convert an alkene to alkyne. That is, we're going to do the function group interconversion of alkene to alkyne so that we can get acetylene as starting material. So once we do the function group interconversion, you can see here how we are going to get an alkyne in presence of, that's the alkene on function group interconversion is going to give rise to alkyne. Okay. Now at this stage we are going to perform the CC disconnection, that is a disconnection between a triple bond, there is acetylene, and the adjacent carbon would give rise to two synthons, wherein there is going to be an anionic acetylene and a cation. Okay. Now the synthetic equivalents for the anionic acetylene anion would be an acetylene group here. So this is nothing but a propine group. So you're going to get a propine here as a synthetic equivalent, and the other cationic synthetic equivalent would be a bromide attacking the carbocation, carbon bearing the positive charge. So these two would be the synthetic equivalents. Now you can see here how there is a propine, and this can be further disconnected. That is, you're going to disconnect the acetylene group with the carbon bearing the triple bond with the carbon having that's the adjacent carbon, and it is going to give rise to an acetylene anion, and it is going to give rise to a methyl group cation. Methyl cation is going to be obtained. Now their synthetic equivalents is again going to be acetylene, and for the acetylene anion and for the methyl cation would be a bromomethane, because Br minus is going to attack the CH3 plus, and it is going to give rise to BrCH3 as the BrCH3 as the starting material. So now we have BrCH3, and also we have the bromomethane, and we have the acetylene as the starting material. Now these two we are going to make use in the synthesis. So again, first step would be acetylene reacting with the NaNH2 sodamide, wherein there is going to be deprotonation of acetylene to give rise to an anionic group here, anionic acetylene, and this would attack the carbon of the bromomethane, and there's going to be the elimination of minus HBr, and it is going to give rise to an intermediate of this kind. So all the synthesis is just similar to the other examples which we just discussed now. So again, you're going to get a propine group. Propine group again is going to be reacted with sodamide, because again we need an anionic acetylide. So this is going to again further react with the bromo group. That is nothing but the alcoholic group here. So here what we are going to do is, since there's a bromine and also there is a hydroxyl group, we are going to protect the hydroxyl group using THP, and then we are going to make use. So now it would not going to, that is the anionic group, that is the nucleophile is not going to react with the hydroxyl group, but it is going to react with the carbon bearing the bromide, and this is again going to eliminate the Br minus. Now after you get the intermediate, you're going to deprotect. That is nothing but acidic medium. You're going to deprotect. So again, it is going to give rise to THP, and it is going to give rise to the alcoholic group here. Now at this stage, we are going to make use, since you have an alkyne here, you're going to make use of Lindlar's catalyst, and you're going to reduce the alkyne to you're going to do the hydrogenation of an alkyne to alkene, and you're going to it is going to give rise to the intermediate of this kind, and this is going to further react with an acid chloride, and we are going to get the target molecule, which is having the ester. So here we have a lone pair on oxygen. It is going to attack the electrophilic carbonyl carbon, because carbon is less electronegative compared to oxygen. So oxygen is going to attack the carbonyl carbon, and then there's going to be elimination of Cl minus, and it is going to give rise to a target molecule of this kind. Now here I have given some more examples. It is having the same mechanism. You can go through this. It is there with the it is there with the disconnection and also with the synthesis. Okay, there's some more examples, similar kind of examples. So this you can make use of whenever you study the synthesis of alkenes using acetylenes. Okay, so thank you very much, students.